to give me a chance to go here. And this is a joint work with H and Yan Zhu. She is at a graduate, PhD student at SJTU, Shanghai Jiaotang University. And first, I would like to talk about the history of designs. So first, classical T design was known, and V is a finite set of endpoints, and Y is a subset with a cardinality K, and Y is a T design if there is a constant lambda satisfying the cardinality of the number, the number of Y which contains T is lambda. And I'm sorry. This is the classical way to write down. So block, the Y is called block and something like this. So classical way to describe the design. And the concept of this classical design was generalized by Del Salt in his PhD thesis to the designs in Q-polynomial association schemes. So X is a Q-polynomial scheme, and this Ri the relation between 2 points in X, and Y is the subset of X, and Y is called a T design if this EI is the primitive idempotence of this association scheme, and EI times phi Y equals to 0 for any I up to T, 1 to T. So here phi Y is the characteristic vector of Y, or sometimes we regard this as a function on X here, and defined by this one. And Del Salt proved the definition of classical T design is equivalent to the definition of T design in K-class association schemes in Johnson scheme. So this D is called the class of the association scheme. Okay. And for spherical T designs, because the Johnson scheme, the character table of the second character table is defined by orthogonal polynomial, and so they extended the idea of T designs to spherical on the unit sphere. Unit sphere in Euclidean space, and Y is a finite set in the unit sphere, and Y is called spherical T design if left hand side is the spherical integral of the polynomials on the unit sphere, and right hand side is just the average of the function on Y. And for this, it holds for any polynomials f, so polynomial of n variables satisfying the degree is up to t. And also we have so we are considering the generalization of spherical designs. We consider a finite set of Y on the union of P concentric spheres. The centers are at the origin, and W is a weight function on Y in positive, and one of the radius could be 0. That means Y contains sometimes the origin 0, and Euclidean T designs are defined by Neumeyer-Seidels paper in here, and the Y and W is a Euclidean T design if this equality holds for any polynomial of f satisfying degree is up to t. And here yi is the intersection of y with the radius of Ri, sphere of radius of Ri, and Wi is the the total of the weight on Yi, and they defined in this paper in 1988 without knowing the result by the numerical analysis, and such kind of concept had been already studied as a curvature formula, and the lower bounds for the cardinality of Y was studied by Miller in 1979, maybe a little bit earlier, but until recently, about 10 years ago, we didn't know his result, and on the other hand, they started to define the concept of relativity design in Q-polynomial schemes. His definition is done in the paper published in 1977, and which is called the generalization of T-design in Q-polynomial schemes. And the relation, I will give the definition later, but the Euclidean T-design and the spherical T-designs, and the relation between relative T-designs and T-designs in Q-polynomial schemes are very much similar. And relative T-designs are defined with respect to a fixed point U0 in X of a Q-polynomial scheme, and for the Euclidean T-design, maybe we can call it a relative T-design with respect to the origin. So first we think about the design in Euclidean space. Euclidean space has a parallel transformation and the rotation, but with this definition, we cannot consider the parallel transformation for this. So if you move it by parallel transformation, then it has no meaning. So, but because of this, maybe this is very good definition, I think. So now we go to the definition of the relative T-designs, and let X be a Q-polynomial scheme, and we use such kind of notation. So U0 is a fixed point in X, and Fx is the vector space of real valued function on X, and this phi u is a characteristic function or a characteristic vector, or sometimes maybe called function of u, and defined by this way. So if x equal u, then 1 and 0 otherwise. And Lix is generated by this ei by u. U is in X. This means that this space is the column vector space of the primitive idempotence ei. And because for the Q-polynomial scheme, the primitive idempotents are generated by in E1, and if we consider this orthogonal decomposition, it is very good to think about. I mean, these Lix are considered as something similar to the polynomial spaces of degree I or something like that. And here, the dimension of Lix is the rank ei is called mi, denoted by mi. And relative T-design in Q-polynomial schemes is defined by Delsart in 1977 in this way. So positive function is a relative T-design with respect to U0 if ei phi and ei, this is the characteristic function of U0, these are linearly dependent for I equal 1 through t. Then we say this function is a relative t design. And non-negative function can be considered a weighted subset of x by the following manner. So y is the support of the non-negative function on x, and define the weight using the value of f on y, phi y on y, and then it is shown on the paper with going to work with H and Etsuko Bannai that the definition given before is equivalent to this definition. So this pair is a relative t design with respect to U0 if this equation holds for any f. Oh, I didn't write any f in. Oh, I didn't write that. Any f in Lix up to t, I up to t, and here the R1 through Rp are the numbers for the shells. We call this XR shell, and if this is y and xr converges, I mean y and xr is not empty, then we pick up R1 through Rp. So this is a set defined by this one, and Wri is the subtotal of the weight function on y and intersection with xri, and we say that in such case we say that y is supported by p shells. So if this equality holds for any function f up to t, lt, L1 through Lt, then we call YW is a relative t design. And each of the cases I introduced here, the spherical or Euclidean or for the Q-polynomial association schemes, the existence theory is the existence is proved. For spherical case and Euclidean cases, Seymour-Zaslavsky in 1984, and the discrete cases, Tiering in 1987, and also some more recent developments. There are some more recent developments, and for any t, if n is large enough, then there always exist designs with cardinality n. And each of the cases, the Fisher type lower bounds are known. So for spherical cases and Euclidean cases done by Miller as curvature formulas. This is much more general than the Euclidean or spherical designs. And for the without knowing his result, there's a Goddard-Seidel paper or there's a Seidel paper or discrete case, Ray Chaudhary. This is not nothing to do with Miller's result. And discrete case is done by Ray Chaudhary and Wilson in 1975. And for relativity designs of Q-polynomial schemes, it is known only for the even t. And in each case, if y attains the Fisher type lower bound, y is called a tight t design. So sometimes relative tight t design or Euclidean tight t design or something like that. And so for Fisher type lower bound for Euclidean 2E design, I just choose the even case. So Mera and decided by this is done by both of them. And if YW is a Euclidean 2E design in Rn supported by the P concentric spheres centered at the origin, then the lower bound is given by such kind of sum. So here Hi is the dimension of the harmonic polynomials of degree I in Rn, n variables. And if equality holds, then we call it a type 2E design, Euclidean type 2E design. And for t equal 2E plus 1 case, this such kind similar to this lower bound is known, but I skip it just for simplicity. And now, if you have a type Euclidean 2 design, just put yi to be the intersection of y with the sphere of radius ri, and let axi yj is the set of the. So this is the usual inner product, and this is the norm of the vectors. This set of this real values for x is not y, then this such kind of result is known. So first, the weight function is constant on each yi for any I, and the cardinality of this set is up to e for any ij, and in particular on each yi. This shows that yi is at most an e-distance set. So distance at most, in number of the distance in yi is at most e. And if p equal 2 and if this is not 0, then yi is a spherical 2e minus 1 design, and the structure, it has the structure of Q-polynomial schemes, and the altogether whole set y has the structure of a coherent configuration. And for simplicity, I mentioned only for the case t equal even, but similar thing is proved for the case of t equal 2e plus 1. Now I will give the definition, talk about the relative T design of Q-polynomial schemes. And Fisher type lower bounds are known. With joint work with AHE, we proved such kind of lower bounds. So YW is the relative T design in Q-polynomial scheme. Then we have the lower bound with this. Here S is the union of P shells, and I defined like this way. And if this equality holds, it is called tight. And in this case, the explicit formula of this right-hand side is was conjectured as this number. These are the rank of EI, and as for this one, the joint work with Suda and Tanaka, we can prove this equality for Q-polynomial schemes with some conditions on irreducibility modules associated to it. And for example, Hamming scheme HDQ and Johnson scheme JND satisfy this condition. I didn't mention here explicitly, but these satisfy this equation. And Xiang proved this conjecture for the case for binary Hamming scheme. And I think it is an interesting problem whether relative 2E designs of Q-polynomial schemes with two shells have similar properties as the Euclidean T designs. Similar means weight is constant or the coherent configuration attaches to it or something like that. And we studied about the weight function first, and for Q-polynomial scheme, and let G be the automorphism group of this the scheme, and if the stabilizer of U0 acts transitively on each shells, then we have this weight constant. This property, weight is constant on each shell. And we think that this the relative T designs on Q-polynomial scheme is very interesting and important, but the research on this subject is not done much yet. So in the following, we introduce the results of relative type 2 designs on binary Hamming scheme for just type 2 design and Johnson schemes, J and P. For the binary Hamming case, this is published in this year, but so YW be a tight relative 2 design of the binary Hamming scheme and supported by 2 shells. So we consider just 2 shells, and the cardinality of YRI is NRI, and the weight is constant. The constant weight is defined by this one, and then the M0 plus M1. So this the lower bound is N plus 1. So it has to satisfy this condition, and the following 1 through 4 hold. So this cardinality is between here, and the ratio is described this way, and the ratio of the constant. And for any integers R1 and R2 between here, the set of the this is the relation in, I didn't define this, but this set is the relation between the 2 points in YRI. So this is given by one integer, and this is the relation between the points in YR1 and YR2. This is also contains just one, and we should have this fraction integer, and also this is integer. So we determined each feasible cases non-existence and existence for any parameters for n less than 30 equal to 30, and if n is 6 modulo of 8, then if there exists Adamar matrix of size 1 over 2n plus 1, then there exists tight relative 2 design on. So it's R1 equal 2 and R2 equal n over 2, and whose weight is this one, non-constant. So W is not constant on Y. Constant on each shells, but not constant on Y. And if n is up to 30, then if Y is not related to not related to this construction, then the weight of the function is constant on Y, and this 30 is improved to 50 by Hong Yue, student at Hebei Normal University, and also there is no non-constant way to type 2 relative type 2 design. So she checked this one up to 50, and I think we should have something like that for in general cases, but we don't have any proof for that. And so this is just existence or non-existence, and we do not have any classification. So, and the classification problem is open, and I think it is interesting to do. Next, I would like to talk about the Johnson scheme's case. So we assume D is less than n over 2, and this is still ongoing research, so I just put it as a fact. This is done by joint work with H and Yen Zhu. And if YW is a tight relative to design on 2 shells, then this is because of the rank of EIs. This has to be n. The cardinality of Y, it has to be n, and this whole. So if D is 2, 3, 4, then there are no tight relative to design of JND or any n. We can prove this one. And if n is less than 30, then there is no tight relative to design for any D less than n over 2. But if we put R2 equal D, then n has to be greater than 2D, and we can calculate this one. So W2 is expressed by this fraction, and xy, the relation between x and y is in here, or here x and y are distinct shells. And so, but we don't know whether they are each of these are just the relation between in this point, or relation between in this point, only 1 or 2, or maybe up to 2, but we don't have the result yet. We are still studying about that one. And but with this condition, R1D over n minus D has to be integer, so we can conclude this one. So there are finitely many tight relative to design of JND supported by R1 and XD for any fixed D. So we can conclude this one. But we are now completing the computation of 31 for n between 31 to 50. And at this moment, we could not find any relative tied to design of JMD, of Johnson scheme. And I would like to give to explain about the proof of the results. So let S be a union of P shells, and let LS be a vector space of real valued function on this shell. And we consider the inner product is using this one. So this is a partial sum on the intersection of each shells. And this is the cardinality of the shells. And for Q-polynomial schemes, it is known if f and g are in LIX, then the product is also in, product is contained in L to I. So if we choose the functions from here, then phi I, phi j is inside this one, and so we can apply the formula of the definition of relative T design. And if we pick up n functions and assume that this restriction to the union of the P shells, if this is an orthonormal spaces of this one with respect to this inner product, then we have. So if with such kind of basis, define the matrix whose rows are indexed by the coordinate by y and having n columns, but, whose entry is defined by this one. Then we have this equality. That means this the matrix is non-singular. It has inverse, and then we have the rank has to be greater than from the rank h should be coordinate of y and this whole. So this is the Fisher type inequality, and so because H is invertible matrix and this hold, we have this equation. So, and this equation we use this equation intensively, and if stabilizers of GU0, stabilizer of U0 in the automorphism group acts transitively on each shells, then this hold for any orthonormal basis. And we have this formula and this equation and this equation, and we use this and this and determine the conditions. Okay. For the the binary Hamming case, we have such kind of fact. So the phi 0 is the column vector of the I and the E0. So this is the constant function of 1, and phi u be the youth column vector of this, and the first the idempotence. Then this set is a linearly independent set on this two shells for any R1, R2 satisfying this one. And using this basis, we construct the orthonormal basis by Gram-Schmidt's method. And this, since each XR for the binary Hamming scheme, it has the structure of Johnson scheme. And in particular, if U and V are in X1, then the relation between them if they are not equal, then it is contained in the relation, second relation. And the computation of this is in terms of weight or these numbers are relatively easier, and we could give the formula given in the theorem, and we have the result. And the binary Hamming case, it is self-dual, and Ki is a coordinate of Xi and Mi is same. And for this is I checked this property for small I'm sorry. So for I is up to maybe 5 or something like that, but this vector, the column vectors span the column space of EI. It seems, but I don't have the proof. therefore, I believe that we can adapt the problems on tight relative tree design of binary Hamming case scheme for E is greater than or equal to 2, but I haven't tried it yet. Now we consider that tight relative two designs of Johnson scheme, and Johnson scheme is also a P and Q polynomial scheme, but slightly very much different. And so in this case we have the dimension equal to n, so the tight relative two design has cardinality n, and as a basis of this one, we can choose the constant function and n-1 column vectors from x1, and x1 is much larger than n, and this case the relation between u and v in x1 is not unique, so it must be r1 or r2. And the computation in terms of these parameters is not easy and very much complicated. We can do some experiments, but to obtain general formula with respect to these values, it's very difficult to say. And in particular, so this ratio is a solution of a quadratic polynomial, and it is not easy to check whether it is a rational number or irrational or irrational with the general formula using this one. So we can make an experiment, and for this case, each shell is a product of two Johnson schemes and does not have a Q-polynomial structure. And for the binary Hamming case, each shell has the structure of Johnson scheme and Q-polynomial structure. So it is known if the relative design is on each shell, defined on each shell, it should be the classical.
How do you define the product of two Johnson schemes?
Just
Some product?
Yeah, the usual tensor product. How do you say? And so Bill Martin defined the concept of mixed block design on product scheme of two Johnson schemes, and constructed some examples of tight ones. So he showed the lower bound, so and have some example of tight ones, and using his results, we can show the non-existence of the tight relative T design for some cases. And construction of tight relative T design seems a bit difficult problem, and we still hope that we can find some examples, though, but we don't have any yet. And so and thank you very much for I will stop. Maybe